Hi, ladies and gentlemen. So today we're going to be learning about the second derivative test. Hopefully you remember me mentioning this to you in class the other day. So we're going to go over it and then there'll be some practice problems at the end. So the first thing I want to tell you about the second derivative test is that the value x equals c has to be a critical point of the function. Well, what does it mean for something to be a critical point or a critical value? So let me remind you of that. So a critical value or a critical point is a value where the derivative at that value is equal to 0 or the derivative at that value does not exist. So in order to use the second derivative test, this must be true. You have to have a critical point at x equals c. Second of all, and this is specifically for Charlie, that the first derivative and the second derivative must exit. Or what we like to say in the world of mathematics is that it must exist. Sorry for my typo. Okay, so let me give you this information here. So if the first derivative and the second derivative exist, then you'll be able to apply the second derivative test. So let's see what that test looks like. So here are the two basic pieces to it. In order to apply or use the second derivative test, you have to have the first and second derivative exist. And if the second derivative is greater than 0, then we say that we have a local minimum at x equals c. And if the second derivative is less than 0, then we know we have a local maximum at x equals c. Remember, we mentioned in class that the reason for this was that when this is true, when the second derivative is positive, you have a concave up graph, which would make then a minimum value. And here, when the second derivative is less than 0, this is creating something that is concave down, which would then in turn create a local maximum. So here's kind of a little graph we're going to talk about here. And take a look at this. If f prime of c is greater than 0, we're thinking about this local minimum at x equals c. So looking at this graph, this would mean, let's get some color here. Here would be a local minimum. This would be because we have a critical value at about 2, so it's where the derivative is equal to 0. And the second derivative would be positive because it's concave up. So that would be one way of checking for a local minimum. So then here's an example of a local maximum. So when the second derivative is less than 0, now remember we already have that critical value, so we already know that the first derivative is 0, so here's my horizontal tangent. So my derivative is equal to 0 here. And then my second derivative is less than 0 because we are concave down, so opening down. So there's my maximum. So what does it mean if the second derivative at a value is actually equal to 0? When you think about this, what would this actually mean? So hopefully you were able to determine that this would mean that we don't really know if we have a max or a minimum. Most likely what we have is some sort of a turning value or some sort of inflection point. And we're going to see examples of this as we move forward in the rest of the lesson. All right, well, thanks for watching, and now you can go ahead and move on to the handout.